So what I was trying to say on this slide here, please make sure that you see some of the parallels. Again, with both the proton and carbon-13 NMR, we want to understand the electronic environment, which will then tell us what is equivalent or non-equivalent. You want to understand the effects that make a group more shielded and therefore upfield compared to a group that's more de-shielded and more downfield. And you can already see, look at that carbonyl group here. It's all the way down near the 200, so it can go even further down. All right, here we have an opportunity to do some analysis, similarly to what we did with the proton NMR examples that I also had on the worksheet that you can find under the certain lecture dates. So there would be September 23rd. We can assign the carbon-13 similarly. What I really want to emphasize here is that these double bonds really, we should think about them as a bond order of 1.5 all the way around because of the resonance that's possible. So if we were to now redraw just one example, we can draw the aromatic ring. We put the circle inside, and then we have a bromine on the right and a bromine on the left. And that we need to understand here that basically we have two axes of symmetry. One is going to go like this, and another one is going to go like this. So we now know that these two carbons are equivalent, and then we can find other carbons that are equivalent. That reduces the numbers. And I highly recommend that you work your way through the other examples that are shown here. So here we have a comparison. So this is very similar to what you learned under proton NMR chemical shift. So now we apply it to carbon-13. Again, the scale is going to go all the way from 0, where you have your internal standards, TMS, trimethylsilane, all the way up to 250. And I've this is something that I created with specialty software. So we want to understand these tendencies. You can see how they correlate to, this is from your textbook, where you see, look here, the sp3 hybridized carbons. They're going to be in the lower areas. Once you introduce some electronegative atoms, such as oxygen, or let's say a halogen, that you will see a de-shielding effect and movement going to the left side. When it comes to the picture, aromatic down here, carbon charge on the oxygen. Resonance helps us understand why we de-shielded. Yeah, so understand the shielding and shielding effects. And again, please do not underestimate the power of doing homework. So you have plenty. So it's really important that you work with all these skill builder components. Plenty of homework, including some. You need to get a good understanding as to what's happening from 0 to 50, and 50 to 100. And it's less about memorizing, but understanding the trends. And as I just explained, resonance can help us understand why carbonyl groups are so de-shielded, right? So try to put that together, that piece of information. And then last but not least, a few words about DEPT-NMR. This is a specialty method being utilized. So we have in regular carbon-13 spectra, we typically just get singlets. And so we don't really know anything about the number of hydrogens. We learned about splitting in proton NMR, and that's really not a good idea for carbon-13. So how can we figure out the number of hydrogen atoms? Well, there is distortionless enhancement by polarization transfer. It's a mouthful. Just know there's a DEPT-NMR, carbon-13 NMR. And it will tell us the number of hydrogens. And then you can work through this. You see that in DEPT-90, which is shown here, here you will only see those that have a methine group, so a CH, and that shows up as a positive peak here. If we look at DEPT-135, and you don't have to understand the background as to why this is 90 and 135. They're just two different components that add to this. Here, we now can differentiate between CH3 and CH. They're going to give you positive signals, but the CH2, this is an even number. That will give you a negative signal, and that is what you see here. Okay, so please make sure you practice with Skill Builder. You have a couple of homework questions that are going to come up like that. You might have a question or two in the quiz for this chapter. So please practice this. And, you know, your textbook is full of examples. I've just picked one. So this is the same material I copied over from the previous slide. A carbon-13 will only have singlets, which is going to be your top one. And we don't look for coupling. So this is called decoupled. So we're going to see a peak for each carbon. I should say that the carbons that have few substituents like this one, sometimes these peaks are weak or small, or not as small as the other ones. And then we have these two methods here. So one of the examples is draw the structure of a compound with a molecular formula C5H10O. And it has, so here you see the spectrum. This is your regular carbon-13 on top. So you see 1, 2, 3, 4, 5 signals, okay? And we have 5 carbons, all right? It says that, and it has